Welcome to section 6.5, rational functions and rational equations. We're going to focus most of our effort in this section on rational graphing. On the screen you can see that I've listed the 5 rules that it takes to do rational graphing. Let's break down each part of it before we do an example to bring it all together. So step 1 is to find the vertical asymptotes. Now an asymptote is a mythical line that our graph will get closer and closer and closer to, but never touch, at least on the vertical side. There's kind of a caveat when it comes to the horizontal asymptote. And vertical means up and down. Essentially, to find the vertical asymptote, we're going to be asking the question of where does the denominator equal 0? And that can happen in one or many spots. Typically, our graphs will have one too many vertical asymptotes. Certainly, it's possible to have no vertical asymptotes as well, but most of these have vertical asymptotes. Horizontal asymptotes are a little more challenging to find, not quite as easy as the vertical asymptotes. So for the horizontal asymptote, what we're going to do is we're going to look at our numerator, and we're going to take the highest power and any coefficient that goes with it. Everything else we're going to ignore. And we're going to do the same for the denominator, the coefficient and the highest power that we see. And then we're going to assess. We're going to look and see which of the two is greater. Is the denominator greater than the numerator? Is the numerator greater than the denominator? Are they equal? Are they the same? As you can see, I've got Roman numerals for these, but in scenario number 1, the denominator is greater than the numerator. If we see that, it means that the horizontal asymptote is 0. 2, the numerator equals the denominator. The horizontal asymptote then is going to be the coefficients of each. And we're going to do examples of this, so no worries. Roman numeral number 3. Denominator is less than the numerator by more than 1. And in that case, there is no horizontal asymptote at all. However, if the denominator is less than the numerator by exactly 1, as in the numerator beats the denominator by a factor of 1, then we have what's called an OA, or an oblique asymptote, aka slanted asymptote. I looked up oblique on Google, and here's the definition I got. Neither parallel nor at a right angle to a specified or implied line. Slanting. So basically, it's a slanting asymptote. So 1 and 2 we haven't seen just yet. But 3 and 4 we have seen, as in what's the y-intercept and what's the x-intercept. Here, to find the x-intercept, we set the numerator and only the numerator equal to 0. And then step number 5, probably my favorite step of this whole process, what we like to call the Achilles point. You know, back in the old days, there was a story about a hero in Greek lore called Achilles. And Achilles was a great warrior, but he had one weak spot. The story goes that when Achilles' mom was pregnant, she went to see an oracle, much like our friend Oedipus's dad did. And when she went to see the oracle told her that she was going to have a great warrior for her son. And she was excited that she was having a son and whatnot, but as a mom would be, she was a little disappointed that he was going to be a warrior, because warriors end up dying. And so she asked the oracle, is there anything I can do to protect my son? And the oracle said, well, if you take your son down to the underworld, or at least where the river Styx comes in, which is where it separates the real world and the underworld, and you dip your son into the waters at a certain time of day and everything else, every part that the water touches will be invulnerable to bladed weapons. And she thought this would be great. And so she took him down there at the appointed time and she dipped him in the river. But she had to hold him somewhere when she was doing it. And so she held him by the back of his ankle, aka the Achilles tendon. That's why it gets that name too. And so Achilles became a great warrior because nothing could hurt him in battle. Until one day he was doing a battle and somebody happened to shoot him from behind into the one spot where he couldn't be hit, his Achilles tendon, his Achilles spot. And he died from that wound. So what we're checking to see is if our graphs have any weak spots. Now, weak spots only occur on horizontal asymptotes. Vertical asymptotes and oblique asymptotes just don't have it. But the way we do it is we check the horizontal asymptote, we set it equal to the function itself, and we see if it can solve. If it solves, it tells us it has a weak point at that x value, and if it doesn't, there is no weak point there. And so that's the steps. 5 steps to do on every one of these rational graphing problems. Now remember, rationals mean fractions. So when you see a fraction, we're going to be talking about rational graphing here. All right, so let's go ahead and minimize these so we have some space to work on, and let's take a look at example 1 on page 479. Find the vertical asymptote and sketch the graph. Now we're going to do more than just find the vertical asymptote according to example 1 on page 479. But let's go ahead and write this down and let's run through the steps. We're going to graph the whole thing. So it says that y is equal to x plus 1 divided by x plus 2 squared. Now there's benefit in looking at it in the original form, which this is, and expanding it. So let's go ahead and expand the denominator as well. So our numerator would stay the same at x plus 1. Our denominator would become x plus 2 squared, which is x squared plus 4x plus 4. So there's value in having both forms here that will help us get what we need to get. All right, let's run the steps here. Step number 1 says the vertical asymptote. The VA, as we like to call it. And it says, where does the denominator equal 0 at? Well, let's go back to the original form for that. We had x plus 2 squared. Really, it means x plus 2. Where does x plus 2 equal 0 at? Well, that's going to happen when x equals negative 2. So that's going to be our vertical asymptote, negative 2. And in fact, x equals negative 2 is a great way to look at it because it is a vertical line. Much like the axis of symmetry when it comes to a parabolic function, which we also say x equals whatever that is, having the vertical asymptote say x equals 2 also works pretty good for us. All right, so there's one of those. Step number 2 is the HA. And for the HA, what we do again is we take the highest powered item from the numerator. In our case, we just have x to the 1. So that's what we're going to have is x to the 1. And the denominator, we do the same. We can look at our expanded form to find that. It looks like we have x squared. If there were any coefficients with these terms, we'd want to take those as well. So if it was like 2x plus 1 in the numerator, we would have 2x down here. But now that we've got that, then we can assess. We go over here and we look at our assessment rules, and they say, which one happens? Well, does denominator beat numerator? Well, 2 in our denominator definitely beats 1 in our numerator. So it means that our horizontal asymptote is at 0. Some people like to say y equals 0, and there's nothing wrong with that either. You can also say that. Number 3 is the y-intercept. What happens when x equals 0? Well, again, back to the original function here. And in fact, the expanded one's a little bit better because if x is 0, that's going to give us 1 in the numerator. And it's going to give us 4 in the denominator. So 1/4. And again, we don't want to just say it as 1/4, right? Our y-intercept is where the x is 0. So we're going to say 0, 1/4. Step number 4 is the x-intercept. And in our case, it's where the numerator and only the numerator equals 0 at. In other words, where does x plus 1 equal 0? Well, it happens when x is negative 1. So our x-intercept is going to be negative 1, 0. And then for step 5, normally we have to check this stuff. But when your horizontal asymptote is 0 and you have an x-intercept, you've essentially already satisfied doing the work on number 5, the Achilles point. This has an Achilles point because it's saying I have a horizontal asymptote, which is a line that nothing can touch, and then yet again I have an x-intercept that's right on that same line. So if you have a horizontal asymptote of 0 and a x-intercept, essentially step number 5 here has been satisfied, and that it does have a weak point here at negative 1, 0. We'll just put it in here again. And that's it. Let's go ahead and graph this thing now. This will be fun. So first we create Cartesian coordinate system, and then we lay in what we know. Let's start with the vertical asymptote here at negative 2. So somewhere here is 1, 2, and there's a vertical asymptote. That's a dashed or dotted line that runs through negative 2 here. So there's my dashed line. All right, we have a horizontal asymptote at 0. Now a horizontal asymptote at 0 is the x-axis itself. We're not going to write this as a dashed or dotted line because the axis itself trumps that. But to make sure that we remember it is a dashed or dotted line at the end of it, I'm going to go ahead and make that dashed and dotted here just to show us that this, while it is an axis, it is also a horizontal asymptote. We know that we have a point of 0, 1/4 here, so if we make this 1, then this 1/4 is pretty small. Right about there is our point. And we also have an x-intercept at negative 1, right about there. So you can see that touches the horizontal asymptote, so that's the part that goes through it. And then that's it, because our weak point we've just seen is right here. Now here's how the graphs go. Every vertical asymptote breaks the graph up into sections. So right now we have 2 sections. We have the section that is left of the vertical asymptote. So that would be from the negative infinity, basically to negative 2 here. And then we have from the right of the asymptote, which would be from negative 2 to positive infinity here on the right. Within that, our graph is either going to be above or below the horizontal asymptote in each section. So we have two sections, so we have two different pieces of graph. It's either going to be above or below the horizontal asymptote unless it goes through the horizontal asymptote. So over here on the right side, let's deal with this first. We have 2 points that are kind of staring us in the face. These points have to connect. And so what we're going to see for this graph is it's going to look something like this. It's going to come like this, then it's going to hit these 2 points, and then it's going to turn and follow this asymptote. Arrowheads at the end of these because it keeps going on forevermore. But then what happens on the left-hand side? It's either going to be above this horizontal asymptote in this section, or it's going to be below in this section. We don't know which. The only way we can do is to pick a test point. Pick a value that is somewhere in this region between negative infinity and -2, and put it into the function and decide whether that tells us it's a positive or a negative. If it's a positive, it's up. If it's a negative, it's down. Now, the last time we did test points, I told you to pick exceedingly big values. This time, we don't want to pick big values. We want to pick a smaller value. So we need to pick a test point between negative infinity and -2. And so I'm going to choose -4. That's a pretty good point to pick here. So we're going to go back to the original form, and we're going to test -4 for x. And again, we really don't care so much about the value. What we care about is the sign. All right. So -4 plus 1 is going to be -3, or for us, that's going to be a negative in the numerator. In the denominator, we've got -4 plus 2, which is -2. But then -2 is squared, which turns into a positive value. And a negative divided by a positive is a negative value. What that tells us is the graph is down below here. Looks something like this. And that's it. There you have it. We just graphed our first rational graphing. Pretty cool, huh?